All right. So last time we kind of introduced the notion of series. We talked about the connection between series and the nth partial sum, right? And we said that when we talk about a series converging, what we're really talking about is the sequence of partial sums converging, yes? It's like the limit, as n goes to infinity, of the partial sums is what's converging, yes? And if it happens to converge to some number, we say that that's the sum of the series, okay? That is the bedrock of everything series, okay? We create the sequence of partial sums, which again is this little thing down here, yes? There's the sequence of partial sums right here. And we take the limit of that thing as n goes to infinity, which makes perfect sense, doesn't it? I mean, it's kind of like the improper integral thing that we were doing before. Like we talked about this, but like an integral from 1 to infinity, f of x dx. We said that this is equal to the limit as b goes to infinity of the integral of what? 1 to b, f of x dx. And then we kind of are dealing with an integral on a finite interval. And we can do our thing with that and take the limit as b goes to infinity. And we do a similar thing here. What we do is we say, look, you want me to deal with the sum, k going from 1 to infinity, a sub k. Well, what I'm going to do instead is I'm just going to take the limit as n goes to infinity of what? Sum going from k equal 1 to n of ak. And this guy right here is what we refer to as the nth partial sum. And we call it S sub n because it reminds you it's a sum, okay? And it's a partial sum that includes the first n terms. Remember, we talk about terms or summands. And one thing that I would remind you of very specifically, okay, so any questions on this before we kind of move on? Any questions? So convergence of the series means convergence of the sequence of partial sums. And we very dramatically last time were talking about this sentence right here, that you will avoid a lot of confusion for yourself if you remember that every series has two sequences associated to it. The sequence of terms in the sum, or summands, right? You have that sequence of things. But then you also have the sequence of partial sums, right? Which basically is just the sum of everything up to that point, okay? Those two things are important, and sometimes we'll flip back and forth between the two. Convergence is primarily concerned with convergence of the sequence of partial sums. But not surprisingly, to understand the sequence of partial sums, sometimes we have to look closer at the terms themselves. Does that make sense? It becomes necessary to look at the terms themselves and to get insight into what's happening there, okay? So we will flip back and forth between the two, and I think that's where a lot of confusion can happen sometimes. All right, what I wanted to do was revisit a couple of series today and introduce you to a concept that's going to be very important for us. I want to look at these two series right here. And we already know what the sum of these things is, right? So what was the sum of the first one? Third. And the sum of the second one was 2. And it turns out both of these series are a special kind of series called a geometric series. They both are of the same category of series. They're called geometric series. Okay, so both of these are called geometric series. Okay, they belong to a category of series called geometric series. Now, how can I tell if I'm dealing with a geometric series? Well, to get from one term to the next term in the sum, you're multiplying by some common number, okay? So for instance, what number am I multiplying by to get from like the second term to the third term in this series? Yeah, you're multiplying by a half, aren't you? Right, so times a half. How about from the third to the fourth? Well, for crying out loud, it's multiplying by a half again, yeah? Now, what about these guys right here? So, and by the way, the same was true going from the first to the second term. I was multiplying by a half, if you think about it, yeah? That's what it means to be a geometric series. Getting from one term to the next simply involves multiplying that term by some consistent number to get to the next one, okay? Now, what am I multiplying by to get from the first term to the second term? If I claim that both of these are geometric, what am I multiplying by? Yeah, a tenth. Okay, a tenth. A tenth. Okay. So for each of these series, like the first one right here, we call the common ratio, or sometimes, right, sometimes just the ratio itself, right? So, I mean, you can kind of put common in parentheses here. The ratio R is equal to a tenth. R is equal to a tenth for the first series. And what is it for the second series? R is equal to a half for the second series. Okay, so this notion of common ratio is the thing that determines whether you're dealing with a geometric series. Okay? And we'll talk about the general form of a geometric series, but the main thing I want to do is focus on these two, and then we will see a pattern through which we can understand all geometric series. Okay? So any questions on this before we move on? Questions? Yeah.
When you said you were multiplying each one by a consistent thing, does that mean it has to be the same number every time?
The same number, you call that R. That's why it's called the common ratio. Yeah.
Also, so with those being convergent, does that just mean that if R is less than 1, then it converges?
Well, we'll see. We'll see. So the question is, what can R be for us to have a sum that is finite? Yeah? For us to have a sum that adds up to a finite number, it isn't like infinity or does some other crazy thing. Well, it turns out that in our exploration, we will answer that question precisely. Okay? Yeah.
What if, like, you're multiplying by a number that's changing as a function of something else, so like it's consistently changing? Is that like another category?
Well, right. I mean, there's the sum of, you know, you're right. There's something else. Yeah. There are lots of other types of series. This is a very specific kind of series. Geometric series, you have to be multiplying by the exact same number every time to get from the current term to the next term. Okay. Other questions? Yeah. Well, let's look at these two series, the 1/3 series and the 2 series. Okay, and we'll sort of sort out what's happening with these guys. So let's go into a whiteboard here. Okay, and here we go. Yeah. Okay, so watch this. So we were wanting to deal with like 1 plus a half plus a fourth, but what's a fourth? A fourth is really 1/2 squared, right? And this guy's really 1/2 to the first power. And honestly, let's just be honest here, right? 1 is actually just 1/2 to the what? That's 1/2 to the 0 power. Yeah, that'll be important later on. Okay, and then it's plus, etc., right? And this is equal to 2, right? But how can we draw this conclusion without cleverness? Does that make sense? Like, we want to avoid being clever. Okay, we had to be clever before, right? So without cleverness, yes, we had to say, okay, I'm going to draw an interval from 0 to 2, and I realized, oh, I'm just adding half again every time or something. Yes, and I kind of visually saw what the answer was. That's no good. We don't want to have to like be clever. Who wants to do that? You know what I'm saying? We'd rather just have some kind of formula that describes everything all at once. Now that in itself, coming up with that formula might involve a little bit of cleverness, but we'd rather just have to be clever once, not like hundreds of times, okay? Let's try to be clever one time, please, not hundreds of times, okay? So help me out here. What's S1? What's like the first partial sum for this? Yeah, that's easy, okay? What about S2? Okay, okay, so I'm gonna be careful. I'm gonna say what 1/2 to the 0 plus 1/2 to the 1, right? And we could write down what the answer is, but I'm trying not to destroy a pattern, okay? Okay, and now S3, of course, is 1/2 to the 0 plus 1/2 to the 1 plus 1/2 to the 2, okay? And what do we want? We want the limit as n goes to infinity of what? Sn. Because this equals the sum of the series in question, yes? That limit will be the sum of the series. Now, look at that. Do you see a pattern emerging here? Let me just kind of rewrite this. This is 1/2 to the 0. Okay, notice that each of these partial sums has like S1, there's one term. S2, there's two terms. S3, there's three terms, yes? Okay. So there is three terms in S3. There is two terms in S2. And so on and so forth, yes? What is the pattern here? Where does the power stop relative to the partial sum we are on? One less than the partial sum that we're on, okay? So Sn is equal, this is the nth partial sum, Sn is going to be 1/2 to the 0 plus 1/2 to the 1, okay, 1/2 to the 2 plus dot, right? I'm getting lazy here, but I mean, you know what dot means. Okay, that just means all the stuff in between, and then I stop this madness at 1/2 raised to the n minus 1. Okay, that is the pattern that we observed in those little beginning cases. And we know that if we were at S sub 37 trillion, then you would stop the powers at 1 less than 37 trillion, which good luck trying to say what number that is. It's like 36 trillion, 999 billion, 999 million, 999,999, right? Okay. So we always stop one less than the actual partial sum index we're on. Now, you might say to yourself, okay, what do we do? That's a gnarly sum that's like growing. There is n terms in this thing, yes? Look at that, there is n terms here, right? It's kind of like computer science, like you start at 0 and you end at n minus 1, right? There is a total of n terms here. So there's a growing number of terms. A growing number of terms is not a good situation to find ourselves in. We'd rather have a nice formula that has a fixed number of terms in it. Well, okay, here's a trick that we can do here. We have a common ratio. What's the common ratio? R is 1/2, okay? Turns out that because everything moves in accordance with this common ratio, one trick that you can do is you can actually just multiply the whole sum by 1/2 and shift everything down by a factor of 1/2. So watch what happens. If I take 1/2 and I multiply it by Sn, think about it. If I do that, it's just going to shift all these terms. Do you see it? Like 1/2 to the 0, what's that going to become? 1/2 to the 1. What about 1/2 to the 1? 1/2 to the 2. Okay, what about 1/2 to the 2? Well, 1/2 to the 3, come on, right? And then you go all the way, and then the last term that you're going to have is 1/2 to the n. Okay, 1/2 to the n. And you might say to yourself, so what? Well, here's the thing. In mathematics, oftentimes you like to create a lot of overlap when you're trying to come up with a nice formula. Because if you can find a lot of overlap, then a simple subtraction makes a lot of junk go away. So for instance, there's like we have 1/2 to the 1 sitting right here. We have 1/2 squared sitting right here. By the way, there's a 1/2 cubed hidden in this little dot, dot, dot right there. Do you know what I mean? And incidentally, this 1/2 to the n minus 1, there's one of those hidden right before that 1/2 to the n thing down there. So you have almost perfect overlap between these two things, except for the first term in the case of Sn and the last term in the case of 1/2 Sn. Okay? And one of the tricks of the trades in math is that when that happens, oftentimes it's useful to subtract because a lot of junk goes away. So if I subtract, what happens? Sn minus 1/2 Sn equals what? Well, the only term that's going to survive from Sn is 1/2 to the 0. See that? Yeah, there's a reason I'm kind of leaving that annoying 1/2 to the 0 in there, okay? And look, what is the only term that survives from the 1/2 Sn part? 1/2 to the n, but does that come with a plus or a minus? Minus. Okay, well, that's interesting. Okay, so now what? Okay. Well, but hang on a second. I have to first think about, hang on guys, I'm gonna check on these people that are in here. Can you guys see me writing on this whiteboard right now? Okay, thank you. Okay, so, thank you. Yeah, thank you guys. All right, so before we take the limit, yes, we want to take the limit of the sequence of partial sums. But look, I have Sn minus 1/2 Sn. I can like factor out Sn. This is the same thing as Sn times 1 minus 1/2. Do you know what I'm saying? Okay, and that's equal to 1/2 to the 0 minus 1/2 to the n. Do you see that? So I can actually solve for Sn. Okay, look, Sn is equal to, what's Sn equal to? 1/2 to the 0 minus 1/2 to the n divided by 1 minus 1/2. You might say, why are you keeping all of this stuff around here? Why don't you just simplify 1 minus 1/2 to be 1/2? Because I'm trying desperately to not destroy patterns, okay? One of the biggest mistakes in mathematics, which by the way is a pattern-seeking game, one of the biggest mistakes is to kind of combine things too soon, because you will fail to discern patterns that are present. So I'm trying hard to not destroy patterns. Make sense? So I get Sn is equal to this thing, which is very interesting. And remember, we want to know what this limit is. And now it seems like we're in a place to actually compute it. Okay? We may be in a place to actually compute this thing. So let me go over to the next page here. Let me rewrite the formula. Sn is equal to 1/2 to the 0 minus 1/2 to the n over 1 minus 1/2. And you know that the sum that we want, 1 plus 1/2 plus 1 over 2 squared plus etc. forever, no stopping, is just equal to the limit as n goes to infinity of Sn, which by the way is just the limit as n goes to infinity of this thing that we have right here. 1/2 to the n over 1 minus a half. Okay. We figured out this like simplified form of Sn by doing all that algebraic trickery that we did earlier. Now, what about this limit? What happens? It's 2. How? Well, 1/2 to the n, what does that go to? That goes to 0. Do you know what I'm saying? 1/2 to the 0, of course, is 1. So it's like 1 minus 0 over, what's 1 minus a half? A half, so it's 1 over a half, which is 2, which is exactly what we expected to get. Do you know what I'm saying here? Okay. Now this formula is amazing because like S1 we knew was 1, right? And usually I like to kind of check things to make sure that the formula is right. What if I plug in n equal to 1? What do I get if I plug in n equal to 1 into this formula over here? If you plug n equal to 1 into this, do I get 1? Think about it. It's going to be 1 minus a half over 1 minus a half, which is 1. What about S2? That's 3/2. Does that make sense? What happens if I plug in n equal to 2 into that formula? Let's kind of talk it through. If I plug in n equal to 2, it's going to be 1 minus 1/2 squared upstairs. What's 1 minus 1/2 squared? 3/4. That's 1 minus a fourth, which is 3/4. So you have 3/4 upstairs, 1/2 downstairs. What's 3/4 divided by 1/2? 3/2. Because the 3/4 and 1/2, the 2 flips up and makes the 4 into a 2. It would be 3/2. Check mark, right? The formula is working. Not that we didn't expect it to, unless we made some kind of algebraic blunder. Yeah? Okay. So what was the next series I kind of wanted to look at? The 1/3 situation. Okay, so let's take a look at that. Okay. So next, I had 0.3 plus 0.03 plus 0.003 plus 0.0003 plus etc. Now let's write this thing down as fractions. By the way, you know in your heart of hearts that this should equal what? 1/3. So we kind of have that in the back of our minds as the answer. Okay? So watch this. Let's write this as fractions. What's the first fraction? 3/10. Okay, plus. Okay, let's write that in a different way though. 3/100ths, let's write it as 3 over 10 squared. What's next? 3 over 10 cubed plus 3 over 10 to the 4th plus etc. Now, let me write this in a slightly different way. I'll write this as 3 times a 10th to the first power, okay? Plus 3 times a 10th to the second power, plus 3 times a 10th to the third power, plus 3 times a 10th to the fourth power, plus etc. Got it? All right, and now let's start thinking about, okay, so look, we want to know what this is, right? So we have to sort out what our partial sums are. So what's S1 here? 3 times a 10th to the first power, yeah? Okay, S2 is 3 times a 10th to the first power plus 3 times a 10th to the second power, yeah? Make sense? Okay. Now what? What's Sn? What does Sn equal? Three times a 10th to the first power, 3 times a 10th to the second power, plus dot, 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 plus 3 times the 10th to the nth power. Yeah? That's slightly different from what we had last time, but it's still how many terms? Still n terms. Still n terms overall. And we know that this sum is equal to the limit as n goes to infinity of the nth partial sum. If we can sort out what this doggone thing is, yes? Well, how are we going to do that? What did we do last time? Yeah, and what was the one thing we did that was clever? Yeah, I'm going to erase some of this stuff. You multiplied by the common ratio, okay? So if we take a 10th and multiply it by Sn, what are we going to get? 3 times the 10th squared plus 3 times the 10th cubed plus ... plus, what's the last term going to be? 3 times the 10th to the n plus 1. And then we notice that there's a lot of overlap. For instance, we see the 3 times the 10th squared repeated. The 3 times the 10th cubed from the second line is in the first line in the ... part. And the 3 times the 10th to the n from the first line is in the second line in the ... part. You know what I mean? Okay. All right, help me out. What do we do now? Subtract. So Sn minus a 10th Sn equals, now when we do that, lots of junk cancels, like this cancels with this. This is going to cancel with something in the ... part. The thing raised to the nth power cancels with the thing in the ... part. What's the only things that survive? Yeah, 3 times 1/10 to the first power minus, right, 3 times 1/10 to the n plus 1, exactly. Okay. And then what we did is we kind of factored out the Sn. Remember that? So we factor out the Sn, and we get, what's left behind if I factor it out? 1 minus a 10th, and I'm carefully trying not to destroy patterns, yes? Okay? So then you say to yourself, and by the way, I don't know, this is just an aesthetic appeal. Like, to me, you see the 3 times a 10th minus 3 times a 10th to the n plus 1. To me, it like makes sense to factor out 3 and a factor of 1/10. Do you know what I mean? Okay, so let me just write, so look, if I say that this is 3 times a 10th and factor that out, what's left behind? 1 minus, the 3's gone, yes, but now it's 3 minus a 10th raised to what power? Raised to the n, yeah, that's exactly right. Yeah. No way, because I haven't simplified, I mean, I haven't like raised anything to a power or anything like that, okay? So there's no destruction of patterns here. Well, so let's see here. What's Sn then? What's Sn equal to? One minus a 10th to the n divided by what? 1 minus a 10th. Okay. So notice, I want to point out a couple of things here. I want to point out, because the reason it's like that is because this guy was equal to this guy, yes? And I simply just divided by 1 minus a 10th to solve for Sn, yeah? I want to point out a couple of things. 3 times a 10th to the first power, right? That's like the first term in the series, isn't it? You see that? 3 times a 10th to the first power. That was the first term in the series. See what I mean? That's no accident. It's no accident that that's what I see sitting right here. Okay? In general, that's the sort of thing that's going to happen. So let me ask you, what does this thing limit to? We know what Sn is. It's sitting right there, and I need to take the limit of this thing as n goes to infinity. What happens to the 1/10 to the n as n goes to infinity? That goes to 0 so that it just becomes 1, right? Minus 0, and 3 times a 10th over 1 minus a 10th. So do you see overall you're going to get 3 times a 10th upstairs. And what's going to be downstairs? 1 minus a 10th, which is 9/10, which is what? A third. You see it? That all comes from that little simplified algebraic form that we came up with for the nth partial sum. Okay? 3 times a 10th is just that first term. The 1/10 to the n, that goes to 0, so that all you're left behind is the 1 minus 0 times the first term. The 1 minus a 10th gives us 9/10. You get a third. Yes? Because I took out a factor of 1/10. Right, you're asking why the power went on the 1/10 went from n plus 1 to n instead. Well, because I factored out not just a 3, what else did I factor out? A 10th, 1 factor of 1/10. And so that took it from n plus 1 down to n. Does that make sense? All right. Let's make the quantum leap to the general situation. Okay? So let's do the general situation. So this is a general geometric series. You ready? There in the last one, we had a 3, multiplied by everything, didn't we? And we had this common ratio. And the power on the ratio started at 1 in the second case, but in the first case, it actually started at 1/2 to the 0. Do you know what I'm saying? So we kind of want to give a little bit of flexibility here. We want to give flexibility to have constants. We want to give flexibility for the common ratio to start, not necessarily with the 0th power or the first power or what have you, but it can really start with any power at all. So the general situation is going to be like this. AR to the m plus AR. Okay, you tell me, how would I need to, what would I have to do to get to the next term if the first term was AR to the m? Yeah, I would multiply by r. So this would be AR to the m plus 1 plus AR to the m plus 2 plus dot, 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 plus, plus dot, dot, dot. Plus dot, dot, dot forever. Okay? It just goes on forever. Okay? And so here, A is just a constant, like 3, because it was equal to 3 in the second case, yes? A was really like 1 in the first case. Like there wasn't a common number multiplied by every summand in the first case other than 1. R is the common ratio, okay? And M is the starting power. It's the starting power. Okay? The starting power. All right, so help me out here. So again, this is going to be equal to the limits as n goes to infinity of Sn, where Sn is the nth partial sum, yeah? So what's S1 in this case? AR to the m, yes? What's S2? plus AR to the M plus 1. Okay, are we comfortable at this point that the nth partial sum means that it has the first n terms, yes? We have the first 2 terms for the second partial sum, etc. Now here's a little thing for your pattern determination thought life. So look, I'm going to put plus 0 and then plus 1, etc. You see, so look, the plus 0, that's 1 less than the subindex on S1, yes? I started at plus 1 when I was on the second partial sum. You guys realize that if I do S3, it's going to be AR to the M plus 0 plus AR to the M plus 1 plus AR to the M plus 2. What is going to happen with Sn? AR to the M plus 0 plus AR to the, AR to the M plus 1 plus dot, dot, dot. Where is this madness going to stop? M plus N minus 1. Interestingly enough, yeah? 1 less than the subindex. That's the highest number that you add to M, yeah? Okay, and you tell me, what do we do? What is the thing that we kept doing before? Like, this is a gnarly, an impenetrable sum as it stands. It's growing in its number of terms. We need something simpler in order to digest what's happening fully, yeah. You want to take the limit, yes, but you can't do it right now in its current form. Multiply by R, yeah? So if I multiply this by R, what happens to the first term? It goes from R to the M plus 0 to R to the, yeah, that's right. What about the next one? M plus 2 plus dot, dot, dot. Okay, plus, okay, what's the last one going to go to? All of these are being raised up by one additional factor of R. So what about the last term? M plus N. Beauty. Now notice there's going to be a lot of things that are in common, like these guys. This guy sits in here somewhere, right? This guy sits in here somewhere, just like before, right? What am I going to do? Yeah, that's right. Okay, so Sn minus Rsn equals, amazingly, tons of stuff cancels. Everything but the first term from Sn goes away, yeah? So that's going to be AR to the M. And everything but the last term from Rsn goes away, and that thing survives not with a plus sign, but with a minus sign. It's going to be minus AR to the M plus N. Wow. And what did we do before? Pull out Sn. So it's Sn times 1 minus R. And over here, I mean, let's just try to be extra algebraically inclined. First of all, I can factor out an A, can't I? Know what I mean? But what else can I get from both of these summands? R to the M. And what's left behind if I factor that out? Well, AR to the M factored out from that just leaves behind a 1 in the first case. And what's the last, from the last thing, all that's left is I've taken out an R, I took out R to the M, what's left? R to the N. Look at this. Sn times 1 minus R equals this thing. Yeah? So what's the formula? What is the formula for Sn? Let's write it down. I'll write it down right up here. Sn equals AR to the M times 1 minus R over 1 minus R. Oops. Help me out here. What are you, okay, r to the what? Yeah, that's really important. All over 1 minus r, okay? There we go. And that we arrived at that just by some algebraic manipulations that were exactly in line with what we did with those first two concrete examples. Okay? All right, now comes the million-dollar question. What is the limit of that thing? Well, I think the answer is it depends. It depends on, because look, n only appears in one place. Do you know what I mean? N only appears right there in the power of the common ratio. Now, if r was like 50, what would be happening to that formula? Think about it for a second. If r was like 50, you would have like minus, okay, and then it would be 50 raised to higher and higher powers. That thing would be obnoxiously going down to minus infinity. Does that make sense? But the bottom would also be negative. 1 minus 50 is clearly negative. Do you know what I'm saying? So overall, this thing would be going to infinity, yes? Now, I mean, a could in theory be negative also. The constant could be negative, but in either case, you end up getting plus or minus infinity, yeah? You get this thing diverges to plus or minus infinity depending on what's going on with a. What about r equal to 1? Because think about it for a second. Technically speaking, I can't have r being 1 because I divided by 1 minus r. But if r were 1, think about it. If r were 1, this would be so stupid. Look at the series. What would I be adding up? It would be 1. It would be a plus a plus a plus a an infinite number of times. Clearly, that diverges. Do you know what I'm saying? If I add 5 together an infinite number of times, I get infinity. If I add negative 3 together an infinite number of times, I get negative infinity, yes? So the case where r is 1 is sort of stupid anyways. R bigger than 1 is going to cause us problems, right? So r bigger than 1, by the way, so r equal to 2 would have caused us problems, correct? Like for the same reason that r equal to 50 was causing us problems. What about r equal to 1.00001? Still a problem. 1.00001 raised to the n, that still goes to infinity. Does that make sense? And therefore, it would kind of give us a limit that would be either plus or minus infinity, depending on the sign of like the constant or things like that. So here, I want to write down some conclusions. What is this limit? Well, it's equal to plus or minus infinity if r is greater than or equal to 1. Does that make sense? So if r is greater than or equal to 1, I get plus or minus infinity. So this is if r is greater than or equal to 1. Yeah? So the conclusion there is that this thing diverges. Okay? What if r was equal to minus 1? Okay, what if r was equal to minus 1? Oops. If r were equal to minus 1, so think about it. We have our formula for Sn. If r were equal to minus 1, it would be like 1 minus 1 if n were even, which would give us 0. Does that make sense? Okay. And it would give us, if n were odd, what would I get? Wouldn't I get, what would I get? If n were odd, I would get 2, wouldn't I? So it'd be 1 minus negative 1, which is 2. But the bottom would also be 2, so those would cancel. You know what I'm saying? Okay? And I would get AR to the M. So if n is even, I get 0. If n is odd, I get AR to the M. But then you say to yourself, wait a minute, that makes sense. Because think about what's going on here. If I put r equal to minus 1, okay? Look, isn't it going to just alternate terms or something? Do you see what I mean? You're going to alternate terms and stuff's going to keep canceling and then coming back and then canceling and then coming back. You see what I mean? And so do I ever get close to anywhere? Does the sum ever get close to any particular thing? No, because sometimes it's 0 and sometimes it's equal to AR to the M. Does that make sense? Sometimes it's 0, then it's AR to the M. Sometimes it's 0, then it's AR to the M. It hops back and forth between those two things. So if R is -1, do I get a diverging or a converging series? Diverge. It doesn't ever get close to any number. It hops back and forth between 0 and AR to the M. Okay? What if R was like -5? Problem. Yeah, if you raise -5 to the n power, that thing is still, that's just going to be wildly obnoxious. Do you understand? It's going to not only be growing, but it's going to be growing like in negatives and positives. Does that make sense? So does the partial sum approach anything meaningful in the case where R is less than -1? No. So what we say here is if R is less than or equal to -1, what do we say? We could probably just say does not exist. This limit does not exist if R is less than or equal to 1. What do we say if it does not exist? We still say the series does what? Diverges. Okay? There's really only one other case to consider. And that's if R is an actual true fraction trapped between -1 and 1. If -1 is less than R is less than 1, what happens? Well, because R to the n, if I let n go to infinity, R to the n is going to go to 0. And so what is the sum going to get closer and closer and closer to as n goes to infinity? The R to the n part goes to 0. So it'll be 1 minus 0 in there. So that's just 1. And I'm going to have AR to the m over 1 minus R. Do you see that? This thing limits to AR to the m over 1 minus R. Which, by the way, what's the AR to the m is what ends up showing up upstairs in the end form of our formula. Yeah? So this thing converges, right? So this thing converges to that particular value that we just came up with if R happens to be trapped between -1 and 1. By the way, there's a cleaner way to say that R is bigger than or equal to 1 or less than or equal to 1, and we get divergence there. What you do is you just say that the absolute value of R is at least how large. So if R is bigger than or equal to 1 or less than or equal to 1, absolute value of R is greater than or equal to 1. And what about this guy? If R is trapped between -1 and 1, what are we really saying about the absolute value of R? It's less than 1. So we get convergence of the geometric series if the common ratio is trapped between -1 and 1. Yes? And we know specifically what it converges to. It converges to this number right here. Yeah? Converges to that number right there. Okay? And so that's like the conclusion with geometric series. Okay, any questions on that? We're going to do an example here at the end, but any questions on that? I think that's pretty cool. You may disagree, but oh well. Okay, so let's see here. All right. So, let's see. Yes. Okay, so let me just kind of write down the formula for us to make reference to. AR to the m plus AR to the m plus 1 plus AR to the m plus 2 equals, right, what did we decide? That this thing diverges if R is an absolute value greater than 1, and it converges to a specific value, AR to the m over 1 minus R, if what? If the absolute value of R is less than 1, yes. And in particular, we could actually say, if it diverges, we could actually say that it diverges to plus or minus infinity, depending on what A and R, and in MR, yes? So that's something that we could be more specific about, but it converges to that value if R is an absolute value less than 1. Okay, so let's do a little example here. What about this? 0.123, 123, 123, 123, etc. Right? You know what the pattern is. Okay, this is a repeating pattern, a repeating decimal pattern. I want to know what this is as a fraction. And I'm telling you, we have the ability to do that now. How do we do it? Well, you write this as 0.123 plus, what do you think the next term would be? 0.000123 plus 0.000000123 plus etc. Yeah? And then I rewrite this as fractions. What's 0.123? What's that? That's 123. Let me write it. Let me take take it 2 steps at once. That's 123 times 1,000th. Yeah? To the first power. Plus, what's the next one? 123 times 1/1000th to the second power. Plus 123 times 1/1000 raised to the third power. Plus etc. So look, in this problem, what's our A, what's our R, and what's our M? A is 123, R is 1/1000th, which, by the way, is an absolute value less than 1, and hence we have convergence. Okay, and what is our starting power? 1. So we immediately say that this thing actually converges to, right, and hence equals, as an infinite sum, as a series, as a geometric series, this thing equals 123. You just take the first term, right? 123 times 1/1000th raised to the first power divided by 1 minus 1/1000. Yes? Which, let's do a little bit of arithmetic here. What's 1 minus 1/1000? 999/1000, right? So this is 123/1000 divided by 999/1000. You know what I mean? So what's this as a fraction? 123/999. Okay? So we just converted that gnarly decimal into its fractional equivalent form. By the way, I could check that, couldn't I? Right? I mean, you could go on your calculator and you could simply do what? What could you do? You could kind of convert back to decimal form by going 123 divided by 999, and guess what will come out? 0.123, 123, 123 repeating, yes? Etc. Okay? Does that make sense? Geometric series are one of the most powerful tools across the mathematical spectrum. It comes up in tons of contexts. It comes up in so-called dynamical systems. It comes up in financial mathematics all over the place. It actually comes up in a computer science context a lot. In the realm of algorithmic analysis, like when you're analyzing how long it's going to take an algorithm to execute. Turns out that these geometric series, and in particular the partial sums of geometric series, just run wild all over the mathematical landscape. So that's why I took an entire hour to kind of invest in our clear understanding of what's happening with these things. But again, the whole, oh, by the way, greater than or equal to 1, here I meant to put that, greater than or equal to 1, it diverges. What you do is you immediately say, okay, I have this geometric series. If the common ratio is an absolute value equal to or greater than 1, what's the conclusion immediately? Diverge. The sum never gets close to any particular number. But if the common ratio is an absolute value strictly less than 1, it converges, the series converges, but you can even say what it converges to, which is a great gift that you don't always have. And it will converge to the first term, AR to the M, over 1 minus the ratio. Okay? And that's it. Okay? All right. Tomorrow, I'll talk about another kind of series that we actually know what it converges to. But that's not always going to be the case. It turns out there's going to be a lot of situations where we will be able to say that a series converges, but we won't be able to say what it converges to. We'll just be able to say, yes, that converges. The number it converges to, and unfortunately, that's just the situation we find ourselves in sometimes. All right, that's it.